Okay, well, let's get started here. We only have a few online at the moment, but I'm sure we'll get more added on since this is the lunch hour for those of you who are on the West Coast. I'm Mark Scardina, and this is the inaugural AskTOM office hours session for the Autonomous Health Framework. And today I have with me Michael Zoll, who's the primary architect of the Cluster Health Advisor, which is an important component of the Autonomous Health Framework. And he will be here to answer any of your questions. And I also have some questions that we can start off with if there aren't any in advance. As is usual, we are not going to be talking about anything specific to SRs or license questions generally, and there's a possibility that in case there is something mentioned that is not yet released, please adhere to the safe harbor statement we have here. So we have everybody muted, so we'd like to just have the questions put forward via chat, and then I will ask those questions to Michael. And we are being recorded, so this will. So if you do put anything in the chat window that is code or proprietary, please be aware that this session will be recorded and will be made available publicly. So with that in mind, initially, I'd like to open it up to any of your questions. If we don't have any initial ones, we've got some that we'll get started with here. At this point, since I don't see any initially, let's maybe I can ask you some, Michael. So first off, what is Oracle's goal in developing the Cluster Health Advisor?
Yeah, Mark, the goal was when we started out doing this was to detect problems that could happen in a clustering environment with shared resources and many instances, or potentially many databases per cluster in real time. I mean, so that was the first kind of goal, real-time detection of problems and also diagnosing them in real time. So from experience, we know that these are hard problems, detecting a problem onset so that one can act. And also a first failure diagnosis is usually a fairly lengthy process that requires iterations. So in order to address that, well, at first specifically in a cluster or in a rack database environment was the prime objective here. I mean, and also the other objective was to basically look through all the data that are normally used for diagnosis and problem detection, and kind of synchronize and combine them, right? I mean, so that was, I mean, let's say you have OS Watch data for each node and database data and AWR and Ash data, and all of them have a different aspect of the system's performance or health. We wanted to combine them and basically run algorithms on that allows us to automatically and early at an early time detect deviations from normal performance or from normal functioning of a database or a cluster, right? So that was the prime goal, and knowing that in a cloud or in a large consolidated environment, the problem of identifying causes and effects and culprit and victims is pretty complicated and time consuming, requires expert knowledge. We believe that SHA can contribute to achieving this goal, right? I mean, so basically pinpoint in a large fleet, in a large consolidated environment, in a large cluster, the components and the targets or whatever, or the databases that have a problem and what's causing the problem without going through iterations of getting data and reformulating the problem. So because in that, yeah, and because if we're doing this, we give operators the time to act and work on the problem rather than just diagnosing.
So a key element to this was the fact that we really wanted to be prognostic with regards to and proactive with regards to detecting these issues versus reactive, which is the typical way in which DBAs have been having to troubleshoot issues with the database.
Yeah, prognostic in terms of early detection of the onset of problems, and then in terms of diagnosis, then immediately find a diagnosis for a particular anomaly that we detect. Yes, I mean, we do prognostics also in terms of trending, right? I mean, there are two types of prognostics. One, you figure out a particular problem early, or you see the onset of a problem, and then the other type of prognostic is based on trending. I mean, trying to figure out when you're at risk of running out of memory, and this type of prognostics is built
Okay.
into.
Okay, great. So sort of as a follow-up here, which types of problems does CHA currently detect? We document this sort of list of problems. Can you elaborate on some of these?
Right. So yes, I mean these are kind of the global sort of categories, and so obviously in rack we look at the interconnect network, because if that fails or is faulty, there are consequences for potentially the entire cluster, which can result in eviction. So we're looking at the interconnect from the point of view of the device, or the adapter, network adapter, device statistics, whatever we can find about the media, right, and whatever we can find about the IPC stack. So we have a range of metrics that we monitor every 5 seconds that would tell us whether we have a congestion issue, whether we're dropping messages, whether the interconnect traffic is slow, and that type of thing. So that's at the interconnect level, let's say at the media level, and at the IPC level in the kernel. The other, and obviously there are connected problems in the global cache in rack, right? I mean, if we transfer data from one instance to another, from one buffer cache to another, and the interconnect is faulty, then that is obviously visible in certain global cache metrics. So we connect these type of symptoms that we find, and then try to find a root cause analysis. So okay, anyway, so this type of problem at different layers in the stack of rack. Now, obviously, we're also looking at not just rack problems, but also database and host issues. I mean, especially memory and CPU problems tend to be an issue also in rack, not only in single instance. If one instance is sick and is swapping, then it affects the other instances in the cluster, for instance. So we're looking at PGA memory, we're looking at the overall host memory and CPU and database CPU and their trends. And we try to figure out, I mean, we try to actually find for any abnormality that we detect, we try to find the root cause, right? I mean, is it this application? Is it a login storm that increases the PGA memory, which brings the system into swapping? So we're trying to find, putting all these symptoms together and chain them in order to make an inference of the most likely, root cause. Same for I/O and storage. Sorry, Mark?
No, go ahead.
So same for I/O and storage performance issues. I mean, this goes from basically looking at ASM metrics and looking at the database wait events that indicate storage performance and health and so on. So we look at that from the database perspective, and from the host perspective, and from the ASM perspective. So we're looking at response times there, wait times, I/O ops, and try to detect anomalies with reference to a baseline. Reconfiguration and recovery, obviously, I mean, reconfiguration is mostly for rack. Recovery is single instance as well. So if we're seeing during an instance join or an instance crash, if we see a reconfiguration or recovery that's taken a very long time and affecting an application, we detect that pretty early, and we're trying to give some advice as to how to reduce these reconfiguration recovery times. I mean, actually, the system is also able to infer whether an instance crashed or a node crashed based on all the patterns that it sees. So So, and obviously workload and session abnormal variations. I mean, if there are too many sessions, more sessions than expected, if there's an abrupt increase in the number of sessions or in the consistent gets or in the whatever table scans, I mean, we look at all these workload parameters or workload statistics that you commonly know as system statistics and session statistics, and try to find abnormalities in this. I mean, abnormalities being, I mean, the mean is higher than expected. There's more variance. There is an abrupt trend, and then we try to trigger some sort of inference from it that allows us to get to a conclusion, right? I mean, so basically by putting all this together, we're trying to eliminate certain problems and focusing on increasing the probability that another problem is actually that a certain problem is relevant. And again, I mean, if you have 4, 5, 6, 10 different symptoms, this problem tries to eliminate these symptoms, group them by, and then basically exclude and eliminate some causes and stress the causes that are actually relevant. I mean, that's in a nutshell, that's what we're doing. So when we're looking at these 5 categories here, we're looking at a slew of web statistics, storage statistics, and database statistics that we actually monitor and synchronize in char, right? And then also it kind of looks at all these as every 5 seconds and then tries to determine whether they're abnormalities or not, and then we tries to interpret these problems as either an interconnect problem or whatever, a CPU issue or whatever.
Sure. Okay. All right. That sounds very interesting. So you mentioned about trying to determine problems, and fundamental to that, is, when I go to a doctor, I have all these symptoms, and you described a number of these symptoms. But what I want to do is find out what I need to be treated specifically. So we've got all of these potential issues. How does CHA perform root cause analysis, and if so, how?
Yes, I'm not sure how far we can go here. So anyway,
sure.
I mean, as I said, we look at all these different signals, over 100. I forget what it is, 150 if you put everything together. We get that in a data point. We monitor that every 5 seconds, and then there's something that looks at whether these metrics and weight events and system metrics, whether they are considered normal or not. So if they're not normal, then they're marked as either too high or too low. And based on these discrete inputs, whether we detected an anomaly on a particular system, let's say a simple one, I mean, we're dropping blocks on the interconnect and something in the global cache is taking too long, right? So these 2 symptoms are inputs to the diagnostic model. The diagnostic model itself uses an approach which can work with whatever input it's getting, and it's driving an inference and increasing the probability that a certain problem that we know of, we basically know when these 2 things these abnormalities are on all these metrics that are in an abnormal state, when they're connected, when they develop in a certain pattern, we roughly know, we know from experience and from our training in the lab that that a particular problem is the most likely. So this is the inference in a nutshell that this diagnostic model performs. So it's based on the number and kind of abnormalities that we detect in all these OS and database metrics, and then it puts them together in a model which is probabilistic. So it raises the probability of something of a particular problem being the cause of these abnormalities, and it eliminates other problems that may have under certain circumstances a similar probability, but given the data that's coming in and given the data that is coming in a time series, we'll be able to exclude certain problems and make certain causes more likely. So that's in a nutshell how it works.
Yeah, so this is the result of our lab training, basically, of the machine learning we're doing in the lab to understand what symptoms actually are actually present, and what is the actual symptom that is actually the root cause, and that determination is we build our models around.
Yeah, that's domain expertise, right? I mean, we
Right,
know that.
exactly.
I mean, yeah, that's domain expertise, so we have to do it in the lab. I mean, there are other ways of doing this, but I mean, at this point, we're doing this in the lab, and that's kind of the most accurate method.
So the customer doesn't need to, the user doesn't need to be a data scientist here. He's just benefiting from the fruits of our machine learning that we do in the lab.
No, this is transparent to the user completely.
Yeah.
I mean, yes.
Okay.
The user sees the results, but doesn't have to parameterize this particular process.
Right. Okay. So obviously, I want to be notified when I have issues, and what we haven't talked about is how does CHA inform me as an admin that it detects some of these issues? Can you touch on that specifically, perhaps in Enterprise Manager Cloud Control or in TFA?
Yeah, I mean, most of these, I mean, there are various ways of publishing the results. I mean, there's an interface, a command line interface that allows you to basically get a history of all these results or the current state. There are events sent out to Enterprise Manager when a particular problem is diagnosed. We always have, for each problem, we have these state changes. I mean, something goes from normal to abnormal, let's say. And then we send a packet of information that includes a problem description, the most likely cause, and an action. We send that in a packet via EVMD to the EM agent, and that ends up somewhere, I think, in the, Mark, you know it better than I do, in the incident manager page. We do have a project where we also sending similar events or via the same mechanism to TFA, which then triggers a collection in TFA, which includes our data, and then publishes it via TFA. So that's already the diagnosed problems that we send with all the supporting information, right? And then and it's presented to TFA. So these are the two basic methods. And then the third method, obviously, is we can use a command line interface that is non-GUI and puts out some HTML reports regarding the currently active problems and the history of problems, when problems start and when they end. Yeah, I mean, so basically a report of the timeline.
So for those of you who are familiar with TFA, and we will have TFA specific sessions in the coming months, there is a new release coming very shortly of TFA, which is versioned 18.2. And as Michael said, that this version, the TFA collector, which is the daemon that runs on each node and watches the log files for errors, is also subscribing to this message framework that Michael was referring to, and is able to collect data relative to CHA problems that are detected, as well as it is able to surface SMTP by email notifications when such problems arise or they actually clear. So you're able to, there's two notifications path. The EM one is not quite there yet. It'll be in an upcoming PSU, and the TFA one is going to be released very shortly in the next few weeks to have this functionality. So you'll be able to get real-time notifications when we detect these problems. Okay, so So which Oracle versions does CHA support?
We started supporting it in 12.2, I believe, right? And so database versions, right? I mean, that means the data collectors and also the problem analysis.
Okay, so so we live in grid infrastructure, but we actually are monitoring the databases hosted there, right?
Yeah. Well, I mean, we live in the grid infrastructure because we're collecting this whole ecosystem of signals, right? And the rack database is just a component within that infrastructure.
So we're collecting information on both the nodes as well as the database instances within that deployment.
Yeah, I mean, as far as the collectors are concerned, we're collecting CPU statistics, we're collecting interconnect statistics, and we're collecting IPG statistics from the kernel and ASM relevant information, right? I mean, that's this is the whatever overall collection method in the grid.
Okay, all right. So which platforms does CHA currently support? Is it available everywhere, or that Oracle is, or is it specific to certain platforms?
Yes, I mean, obviously Linux. I think we're supporting Solaris. I believe we're supporting AIM and also Windows. I think that pretty much covers it. So.
Okay, so but in 12.201, we initially are supporting Linux, right?
Yes, yeah. I mean, in 12.201, only Linux. Yeah.
Right. So as we move forward, we're planning on doing more platform support.
Yeah, we're testing on Solaris and AIX and
right.
go along.
Okay. So does CHA require special licensing or EM pack or diagnostic packs, anything like that?
Not that I know of. I mean, you said we're not talking about licensing, but
right. Well, this is
yeah, it's part of the clusterware, right? I mean, it comes up as a clusterware resource, and then I mean, I think it comes up, and correct me if I'm wrong. It comes up when you install clusterware. It's installed. I mean, when you start the clusterware, the course is started, and then
so I can answer this one, but yeah, we only require the rack license. Basically, the bits are there, but basically they actually will not work unless you are running a rack instance, as Michael said. And even though we're getting ash data and data that you would normally get if you had the ADDM option or certain options in the database, we don't require you to have any specific database option besides the rack option to make use of the functionality. And that can be rack or rack one node. It doesn't matter, but it can't be a single instance license. It has to be a rack or rack one node license. Okay, so does CHA work on Exadata and ODA?
Yes, it does. In Exadata, we're looking at all these cell statistics, and on ODA, we're looking at, I think there are no specific port-specific things here. Now, on Exadata, and I believe also on ODA, we require, and it shows up in the screen here, we require a post. It doesn't automatically install when the GMR is installed. It has to install the GMR, which is the management database. I mean, we haven't talked about it yet. It's the repository basically, and so basically there's a post installation step on Exadata, and I believe also on ODA, right? I mean, we always wanted to change that, but that's not yet done.
Yes. So currently in 12.201, as Mike said, because the management repository is not part of the base Exadata image, customers have to do a post installation of the management repository and configure the resources for CHA, but that's fully doable, and we fully support that configuration. It is new functionality that Exadata hasn't yet incorporated into their images, but right now it is a supported configuration, and we do have customers using it in that way. And otherwise, we've got a standard CHA deployment, and there's nothing sort of unique about Exadata or ODA that precludes using our functionality. Okay, so what data does CHA use to detect these issues? You mentioned a bit about the data, but can you get a little more specific here?
Yeah, sure. I mean, I think it already became clear. I mean, let's start from the database. I mean, we're collecting system statistics and session wait events and PDB statistics. So instance level system statistics and PDB system statistics and wait events, which are collected by a directly from the database. Maybe one thing that we should also mention is talking about the database is that we're not using SQL. I mean, when we're talking about system and system statistics and wait events, for instance, these are the two main classes that are used also by AWR and by other diagnostic tax and performance tools. These tools tend to query $, tables, which we don't do. We're reading this data and its equivalent directly from memory and buffering it in memory and without writing anything to disk during the collection process and also during the analysis process. So that's there's a difference in how we collect it, but not a difference in what we collect. I mean, it's pretty much the same data with a little bit more precision because we're collecting data from the database every 1 second and we're kind of rolling it up to 5 seconds. So that means you're getting more precision even than with ASH. And we're looking at also additional data which ASH doesn't expose in order to get our samples very accurate. So anyway, so that's system statistics in the database, physical reads, consistent gets, DB block gets, table scans, fetches via table scans, fetches via row fetches via index scans, and so on and so forth. I mean, you're probably familiar with it. If not, these are a few examples. So that's the database. Yeah, go ahead.
And then from the node?
Yeah, from the node, we're looking at we're looking at CPU data. We're looking at process CPU consumption. I mean, there's a product called CHA in pre-12.1. I think it still exists, and we still have it as a product.
Cluster Health Monitor, CHM.
Yeah, we're using pretty much all the data that it collects, that CHUM used to collect, and it's a kind of equivalent. I mean, if you want an equivalent, it's kind of equivalent to what OS Watcher would look at. I mean, it would look at VMstat, it would look at IOStat, and other categories of data and IPC statistics. So we're looking at mostly the same data from the host interconnect and storage perspective, right? I mean, that kind of broadly classifies it.
Yeah.
Now, the one thing that we do need to stress is that all this data is synchronized through these 5-second samples, right? I mean, so what we're receiving is actually a synchronized sample of all these statistics in one data point, right? And that's what the detection is based on.
Okay, all right. So with all of these statistics, how expensive, I mean, generally speaking, you know, that fine-grained statistics can produce a significant amount of overhead in my systems, but so how expensive is this?
Yeah, it's not very expensive. I mean, we're doing this analysis every 5 seconds, and since it's all in memory, it is less than let's say 2% of a CPU. I mean, actually even less in terms of CPU, and the memory consumption is I believe it's about for a sizable cluster is negligible. It's about 200 megabytes, and it doesn't leak, it doesn't grow. It's pretty much steady at 200 megabytes, regardless of the number of targets. There may be slow variation, but that's what we measure in a relatively large cluster. So I mean, so from the memory and from the CPU perspective, the overhead is very negligible. I mean, 1%, 2% of the CPU is definitely, I mean, over time, right? And it's definitely low overhead.
Okay, yeah. Well, and the fact that we don't have to maintain a database connection to get this data takes us out of the transaction paths and do not interfere with any of the work going on in the database, right?
Yeah, I mean, the other thing is, I mean, that we basically optimized it because, I mean, some ASH data is already on system statistics already collected. Hang Manager does something. We kind of piggyback on other collection mechanisms when we can, where we can.
So we actually didn't introduce new collection mechanisms into the database. We're just basically leveraging what the database is already collecting.
Yes, exactly. I mean, that's one thing. I mean, we're leveraging all the common system statistics. We're just reading them from memory, and we're trying to piggyback, as I said, we're trying to piggyback with existing in-memory APIs to collect the statistics.
Okay, all right. So as a user, can I actually examine and review this analysis to sort of validate what CHA is detecting and diagnosing?
Yes, I mean, we have. Let's see what we produce. We're producing pretty much. We're producing pretty much from the. We didn't really specifically talk about it. What we're producing is a problem statement. Basically, we detected this problem, its cause, and its action. So we store all the relevant information. I mean, the values of the statistics that the analysis is based on, and the state of the so-called fault detectors. I mean, those things that detect anomalies, we call the fault detectors. So we store all that in the management database. Now, that information is accessible partially, I mean, via, well, you have it there, charctl. I mean, there are two ways of extracting the information. One is this charctl, I think it's dump diagnosis or something like that, or query diagnosis, I'm sorry.
Right.
So we're getting from there, we're just getting the problems and the causes and their actions. So that's the high level first, first cut. Now, if we want to look at all the evidence that is used in order to derive these conclusions and diagnoses, then we can export the entire repository, and we can limit it by time ranges and so on and so forth. So that's one way, which produces a file which we call the MDB file, and then that can be used as an offline diagnosis mechanism. And then there's the GUI here, which you kindly just brought up, which is materializing all the data visually. And the good thing about this is, so this can be used, this GUI can be used, but let's stick with the offline first because we mentioned that. So we export the repository and we load all the data into this particular GUI, and what you see here is a sample of this, and basically you can scroll through all the data at the host level, at the database level, and at the instance level, and view all these findings here. And so this is an example of a problem that we detect at the IO level, at the IO layer, and so it gives us the cause here. As you can see, it gives us at what time it started and the corrective action, and well, we have this is also giving us kind of an inference chain, and basically also the supporting information here, right? I mean, so we're looking at all the signals that are high that we're interpreting as that we use to derive or infer this diagnosis. So you can see that here. This is the actual expert mode, right? To see it, so you can study the actual characteristics of the entire statistics, and you can switch it back into a mode where you just see red and green as you see that in the, yeah, here you go. So you can basically see red and green, which basically means at that point, during these intervals, during these periods, a particular statistics was considered abnormal, right? I mean, either it occurs too often or it's too high, that type of thing. So that's the GUI basically that allows you to inspect the data that is used for the inference process, including the inference that we make, right? I mean, the inference is the text that you see.
So I'm actually able to drill down and do a bit of exploration on my own to get comfortable with our own CHA's diagnosis and validate whether or not we're doing the right thing.
Right. I mean, maybe one thing that we should stress again is that we kind of started with the offline paradigm. So that's basically just export the repository after you've had a problem. When you have a problem, use the GUI. This GUI is also can make a SQL connection to the management database, and then basically combine a historical mode and an online mode, right? I mean, so you basically see these findings advance in time here. So it can be used in online and in offline, in an offline capacity without, a without any change in parameterizing the GUI.
Yeah, but in the online mode, I do need to, in the live connection mode, I do need to run the utility local to the cluster versus having it on my laptop, as an example.
Yeah, I mean, this tool we just basically, when Thomas wrote it because of the need to inspect all the data in totality and correlate it with things, and it has to be fast, it has to be quick, and it's a good data discovery tool which is downloadable.
Yeah. Okay, and here's the Moss note that you can download it and we will be updating it as needed. So we've been talking about database workloads as if they're sort of a generic entity, but when I do an install of a database, I pick the type of database, whether it's a general purpose database, whether it's designed for DSS, BI, is CHA tuned to specific workloads or a database type, or, what's the...
No, I mean, we don't see a need to do that. I mean, we have a generic model that is installed basically that is the base model that we train in the lab, and we train it through different phases. And for engineered system, it's pretty precise. And so, and there's no specific workload or DB type used here. We are using a mix of applications in order to generate the data with which the model is trained. So now, when we're talking about model, then we have two parts. I mean, one is the diagnostic model. There's no specific, diagnostic so you can take one model and load it into something else, and the diagnostics is going to work for DSS or OLTP or Exadata or whatever. So in terms of its failure modes, the other thing is the training of the detection of the abnormalities, because we have to have a notion of what's normal and abnormal. So that is trained in the lab, and that is also not specific to workload, because the model itself that you train is kind of, and again, I'm going out on a limb here, it's kind of like a clustering model. So it basically it kind of summarizes all the states that the database and its performance statistics can be in, or an OS can be in. It summarizes those very flexibly, right? So it's able to adapt to different workloads and find workload or seasonal specific patterns, right? And have them. It's not, and even the fault detectors are trained not to use thresholds. I mean, they're basically using trends and sequential analysis in order to have a confidence detection. So from that point of view, no, it is not tuned to specific workloads or DB type or DB types. So, I mean, at least not when it comes to you for the first time. So.
But can I actually increase CHA's sensitivity to my specific workloads?
Yes, I mean, you can. I mean, you will probably find that certain statistics like consistent gets, physical reads, and so on and so forth are specific to your workload or seasonal patterns or something like that. And then, although this in itself may not result in any detections or faults or abnormalities, it would just not track your workload properly, right? And then you can there's a way of using, and again, a command line interface here. There's a way of training the model and adapt it to your specific workloads, and you would do that in those cases where you either have a lot of alarms that you think are false, or if you have a lot of deviation from your actual workloads in what we predict, right? So again, you can correct it by just specifying a time range of where your system, your component, your database was behaving normally, and that is then formed into a model and then stored in the management database and reloaded the next time you start monitoring.
I see. So you were mentioning about using the detection mechanism and the notifications as a way in which to determine when I should calibrate. Can you go into a little more detailed. Should I calibrate to make the models more sensitive, to make the models less sensitive? You know, what guidance can you give me with regards to whether I should calibrate or not?
Yes, I mean, we do have a, we do try to keep the sensitivity level at a very generic level. I mean, there's always a trade-off in everything you do with this type of approach, right? I mean, there may always be a bias towards something. You may overfit, you may underfit. So we try to avoid that by making our models as generic as possible. If we miss alarms for any chance, we would allow the system to be retrained, right? I mean, so if there's something we don't detect that requires recalibration, right? I mean, because it's potentially a mismatch between our model and the actual system or configuration or whatever that we're running on. So that's one thing. So we're making it a little bit. We can make it more sensitive. Now the other thing is, and you'll find that in general, you'll find that by looking at the data, let's say in that GUI that Mark pulled up here, you would eventually see what the observed value, what the predicted value is, and if that is a big, it's actually visually quite interesting. If that difference of the residual, let's say statistically, is sort of the difference between the observed and the statistic data on some of the let's say load statistics, then you may yeah, we're gonna potentially see it here. Yeah, I mean, so, for instance, there, yes, I mean, yes, disk latency, it's a good example. I mean, it's showing us here the expected value is 25 milliseconds, and the what is it, 100 milliseconds, if I read that right, is what we're measuring currently. So there's a big difference in residual. If you see that difference being big, I think the blue line here is the predicted value, and the red line is the actual observed value, if I'm not mistaken. Here, I can't see it that well, but I mean, I think that's what it is. Then you'll say, there's here. I mean, if this may you could argue that this is out of range, and it needs to be recalibrated because the blue line is so low, the residual is so big. It could also be
if I felt that this was normal behavior, right?
Yes, yes. If you see, yes, exactly. Now, yes. I mean, one thing is maybe also interesting because I mean, here, I mean, those latency statistics and whatever disk performance is, they usually, if this IO subsystem scales, you'll probably never have to recalibrate it because I mean, they're usually within those boundaries that we define in our base models. If you see things like consistent gets, IO ops, and so on and so forth, if you see them, if you see a high residual on those, you know that your workload changed and you may want to recalibrate, right? So there's also a possibility that our predictions are actually higher than the actual observed load. That means, well, we may have a lot of.
So if my blue was way above my observed value, that would indicate that we were predicting a lot poorer performance than we were actually getting, and therefore there could be defects that we wouldn't detect because we think they were normal.
Right. I mean, in that case, I mean, to go back to the argument, in that case, it would be less sensitive. We would probably miss alarms because we're basically predicting them with a larger margin than expected, right? And so that's one way. So these are a few ways to figure out when to recalibrate.
Sure.
I mean, we hope it's not happening that often, but again, I mean, I just want to make sure that I mean, that people understand. I mean, normally IO statistics are pretty constant and stationary in their values, right? I mean, you probably never have to recalibrate something like ASM latency 100 milliseconds, expected 25. I mean, so you probably know that this is not normal, and you should necessarily accept it as normal. On the other hand, other statistics like consistent gets, physical reads, everything that you know from the database perspective, for instance, that is load specific, they may over time deviate, and you'll see that because I mean we'll find potentially abnormalities in that, and if those abnormalities are actually false alarms in terms of the load, it just developed that way. It's more load on the system because you put more load on, then you'd have to recalibrate.
Okay. All right. Let's go back to. So at this point, do we have any questions from the participants? So far, I haven't seen any. additional questions here, but we'll open it up. We're getting near the end here, and want to make sure that we've answered everything. I think this has been quite a informative session about sort of under the hood of what's going on with Cluster Health Advisor. We are recording this session, so people can actually access it after the fact and gain the insights without actually having to be here. But if any of our participants have any further questions, please type them in the chat. And if not, we will be having, this is our normal session time, the fourth Tuesday of the month at noontime Pacific or 1900 UTC. And so we will be having a session upcoming in June. And please subscribe to the Autonomous Health Framework office hours, and you'll get notifications for these sessions. And I do encourage you, because there are a number of components in the Autonomous Health Framework, we're trying to actually cover across all of them, and so we'll sort of have dedicated sessions to each one, and the upcoming one will be in more in the recovery area, in the TFA and OraCheck areas, and so please tune into that in June. And if there's no other questions, I'm signing off. And thank you, Michael. This was most informative, and we appreciate your time here.